We are now in the fourth lecture of our lecture series on optimization theory. In this lecture, we shall be dealing with the search techniques. The following search techniques are of interest. 1. The dichotomous search technique. 2. The golden section search technique. 3. The Fibonacci search technique. And 4. The Newton's search technique. The first three of the above techniques are the direct search techniques, while the last technique is the gradient-based search technique. To apply any of the above search techniques, we assume that the function f of x is unimodal. The general idea of the direct search technique is to identify the interval that contains the optimum solution point. Then try to locate this optimum point by iteratively reducing this interval to a desired degree of accuracy. These intervals are known as the interval of uncertainty. The algorithm for direct search techniques. For a minimization problem, the sequence of steps are as follows. Step 1. Identify the initial interval of uncertainty, the interval I equal to A to B. Step 2. Choose 2 points, x1 and x2, in the interval AB, such that A is strictly less than x1, x1 is strictly less than x2, and x2 is strictly less than B. Then evaluate the value of the function f of x at these 2 points. Step 3. If f of x1 is less than or equal to f of x2, then choose the interval A to x2 to be the next interval of uncertainty. Otherwise, choose the interval x1 to B. Step 4. If the length of the ket interval of uncertainty is small enough, then stop. Otherwise, return to step 2. Dichotomous search technique. In a dichotomous search technique, the point x1 and x2 are selected such that they are at the same distance from the midpoint M of the interval of uncertainty. Thus, if the initial interval of uncertainty is the interval AB, then the point x1 is chosen to be m minus epsilon all over 2, and x2 is m plus epsilon all over 2, where epsilon is a very small positive number arbitrarily chosen, and m, as the midpoint of the interval, is a plus b divided by 2. We illustrate this with the following diagram. This is the interval AB, and this is the midpoint of this interval M. We choose the point x1 somewhere here. This is the point x1, and this is the point x2. The point x1 is chosen in such a way that the distance of x1 from the midpoint M is epsilon all over 2. And x2 is also chosen in such a way that the distance of x2 from M is also epsilon all over 2. The length of the initial interval of uncertainty is defined to be L1 equals to B minus A. The second interval of uncertainty will therefore be either I2 equals to the interval from A to x2, or the interval I2 equals to from x1 to B. And the length of this interval is L2 equal to x2 minus A or B minus x1. If we substitute for x2 here, which is M plus epsilon all over 2, then minus A, that will give us the length of the second interval L2 to be half into L1 plus epsilon all over 2. Please recall that M is A plus B all over 2. So A plus B over 2 minus this A will give us B minus A over 2, which is equal to half L1, then plus this epsilon all over 2. Similarly, if you substitute for x1 here, we will obtain the same result. The length of the third interval of uncertainty can be obtained in terms of L2 as follows. L3 equals to half L2 plus epsilon all over 2. If we now substitute for L2, we can express L3 in terms of L1 as half into L2 is half L1 plus epsilon all over 2, then plus this epsilon all over 2. If we open this bracket, we will now obtain 1 over 2 times 1 over 2 L1 is 1 all over 2 to power 2 L1 plus half times epsilon all over 2. That will give us 1 all over 2 to power 2 epsilon, then plus epsilon all over 2. Similarly, we can obtain the expression for L4 to be half L3 plus epsilon all over 2. Now substituting for L3, L4 will give us 1 all over 2 into 1 all over 2 to power 2 L1 plus 1 all over 2 to power 2 epsilon plus epsilon all over 2, then plus this epsilon all over 2. Opening this bracket, this will give us L4 equal to 1 all over 2 to power 3 L1, that is multiplying this half by this 2 to power 2, will give us 1 all over 2 to power 3 L1. Multiplying this half by 1 all over 2 to power 2 epsilon will give us 1 all over 2 to power 3 epsilon, plus multiplying this half by epsilon all over 2, that will give us 1 all over 2 to power 2 epsilon, then plus this epsilon all over 2. We can continue this way until we get to the length of the kth interval. So by induction, we have Lk equal to 1 all over 2 to power k minus 1 L1 plus 1 all over 2 to power k minus 1 epsilon plus 1 all over 2 to the power k minus 2 epsilon plus and so on until you get to epsilon all over 2. Please observe the pattern. For L3, we have the coefficient of L1 to be 1 all over 2 to the power 2. That's the power here is 1 less than this 3. For L4, the power here is 1 less than this. The power here is 1 less than this. Then from here down, the power is in a decreasing order. So in general, for Lk, the power of L1 will be 1 less than this, which is k minus 1. And the power of epsilon here is k minus 1. Then the next power will be k minus 2. The next will be k minus 3 until we get to the power 1. This is equal to 1 all over 2 to the power k minus 1 L1 plus, observe that epsilon through here is common, so we can factor it out. When we factor this out, this will give us epsilon into 1 all over 2 plus 1 all over 2 to the power 2 plus 1 all over 2 to the power 3 until you get to 1 all over 2 to the power k minus 1. Observe that that series is a geometric series. So we can apply the formula for finding the sum of the first n terms of the geometric series to obtain 1 minus 2 to the power k minus 1. So therefore, Lk equals to 1 all over 2 to the power k minus 1 L1 plus epsilon into 1 minus 2 to the power k minus 1. And this is true for k starting from 1, 2 to infinity. Example 1. Let us solve the following minimization problem. Minimize f of x equal to 2x squared minus exponent x over the interval 0 to 1 with an error in the optimum point x star of not more than 0.05. That's, we have to choose our epsilon to be equal to 0.05. Solution. First, let us obtain the midpoint of our interval of uncertainty. The initial interval of uncertainty is 0 to 1. So this is our A. A is 0 and B is 1. So the midpoint is m equals to a plus b over 2, which is equal to 0 plus 1 divided by 2. And that will give us 0.5. So we are now ready to choose our first point x1, which is equal to m minus epsilon all over 2. And that is equal to 0.5 minus epsilon is 0.05 divided by 2. That is 0.5 minus 0.025. And that will give us 0.475. The second point x2 is m plus epsilon all over 2. That will be 0.5 plus 0.025. And that will give us 0.525. Now let us evaluate the value of our function at these 2 points. At the point x1, f of x1 is equal to 2 times 0.475 raised to the power 2 minus exponent 0.475. And this will give us minus 1.157. The value of the function at x equal to 2 is f of x2 equals to 2 times 0.525 squared minus exponent 0.525. And this is equal to minus 1.139. Observe that f of x1 is strictly less than f of x2. So this implies that our second interval of uncertainty, I2, is from A to x2. Remember, our A is 0 and our x2 is the point 0.525. So this will be our second interval of uncertainty. Now, using this second interval of uncertainty, the midpoint again is a plus b over 2, which is equal to 0 plus 0.525 divided by 2, and this will give us 0.2625. Then our point x1 is m minus epsilon all over 2, which is equal to this minus 0.025, and that will give us 0.2375. x2 is equal to m plus epsilon over 2, that is m 0.2625 plus 0.025, and that will give us 0.2875. If we continue that way, we will generate this table. This our K stands for the number of iterations starting from 1, 2, and so on. This is the left limit of our interval of uncertainty, while b is the right limit. This column is for x1, this column is x2. This is the value of the function at x1, this is the value of the function at x2, and this is the length of the kth interval of uncertainty. So what we have done illustrated before, we obtain x1 to be 0.475 and x2 to be 0.525. f of x1 is minus 1.157, f of x2 is minus 1.139. As you can see, this is less than this, and the length of that interval is 1. That is 1 minus 0 is 1. Since this is less than this, that means our next interval of uncertainty will be from a to x2. Remember, our a here was 0, so we take 0, then the b will now be x2, which is 0.525. Now, using this interval of uncertainty as our working interval, the midpoint of this, from there we will generate our x1 to be 0.238 and x2 will be 0.288. f of x1 is minus 1.155, f of x2 is minus 1.168. Clearly, this one is greater than this. Since this is greater than this, our next interval of uncertainty will be from x1 to b. This is our x1, which is 0.238, that's this one, and to b is 0.525. The length of this interval of uncertainty is this one minus this, which is equal to 0.525. Now, using this interval of uncertainty from 0.238 to 0.525, we obtain x1 to be 0.357, x2 to be 0.407. Then f of x1 is minus 1.74, f of x2 is minus 1.71. The length of the interval is 0.287. That is this one minus this. As you can see here, this value, this figure, is less than this. So our next interval of uncertainty will be from a to x2. So this is our a, that's 0.238, and our x2 is 0.407. So this will be the next interval of uncertainty from 0.238 to 0.407. Using this interval now, we obtain x1 to be 0.298, x2 to be 0.348. The value of f of x1 is minus 1.169, f of x2 is minus 1.174, and the length of the interval of uncertainty is this one minus this, which is equal to 0.169. Clearly, this figure is greater than this. So our next interval of uncertainty will be from x1 to b. Here is x1, which is 0.298, so that will be our a, and our b is 0.407. Using this interval, now will give us x1 equals to 0.328, x2 equals to 0.378, f of x1 is minus 1.173, f of x2 is minus 1.174, and the length of interval is 0.109. This figure is greater than this. So our next interval of uncertainty is from x1 to b. Here is our x1, which is 0.328, and b is 0.407. Now, using this interval, x1 is 0.343, x2 is 0.393, f of x1 is minus 1.174, f of x2 is minus 1.173, and the length of interval is 0.079. This is less than this, so our next interval of uncertainty is from a to x2. Here is our a, which is 0.328, and our x2 is 0.393. So this is now our next interval of uncertainty. Using this, that will give us x1 to be 0.336, x2 to be equal to 0.386. Then we obtain f of x1 to be minus 1.174, and f of x2 is minus 1.173. The length of interval is 0.065. This figure is less than this, so our next interval of uncertainty will be from a to x2. Here is a is 0.328, and our x2 is 0.393. This figure is less than this, so our next interval of uncertainty will be from a to x2. Here is our a, which is 0.328, and here is our x2, which is 0.386. So this will then give us this new interval of uncertainty from 0.238 to 0.386. We can continue this way until we get to the last interval of uncertainty, which is equal to 0.333 to 0.383, with x1 equals to 0.333 and x2 equals to 0.383, with the functional values at minus 1.173, and for x2 minus 1.173, and the length of the third interval of uncertainty, that's the 13th interval of uncertainty, is 0.50. Clearly, we have been able to reduce the length of the third interval to the required or the desired accuracy, which is 0.050. So we can end the algorithm at that point.